This lecture, we will study the finite shear strain. Consider a fiber in which a very short length, okay, the fiber with a very short length, dx1, and another one, dx2. You see, the angle between them is 90 degrees. Now, after the deformation, these lines, will have this line we call L1 corresponding to dx1, and the blue one, L2, corresponds to dx2. And this theta is the angle between these deformed lines. Now, let's consider the unit vector n1 and n2, the unit vector n1 and n2. So L1 is dx1. So L1 is the line, is the deformed line in which initially the length is dx1. And L2, dx2, is the deformed line in which the initial length was dx2. Now, let's focus on the unit vectors n1 and n2, correspond to the line L1 and L2. Now, n1 is the vector dx1 divided by the magnitude of the x. Now, look, focus only in this line L1 over here, okay? Forget the line L2. Now, the vector dx1, dx2, but dx, the vector, is related to the deformation gradient f dot dx1. dx1 is the initial length, dx1, the initial length in the undeformed configuration. Now, dx1, this vector x1, is the unit vector e1 times the initial length L0. See, L01 is dx1. So let's focus only on this line, which the unit vector is n1. So n1 is f, the second order tensor dot dx1. dx1 is the length dx1 times the unit vector e1. This is this. Now, let's come to the unit vector n2. The same. n2 is a vector, is the deformed vector dx2 divided by the size of dx2. dx2 is the length L2. You see? The same. And now, this vector dx2 will be equal to this vector here, f dot capital dx2. Capital dx2, you see, is the length dx2 times the unit vector e2. Now, from the last lecture, we saw what we call the stretch ratio. Okay? Ratio. The stretch ratio is dx divided by capital Dx, or L divided by L0. Okay, this is equal. Now the square root of ni dot the second order tensor g dot d. You see, where g, don't forget, g is equal to L plus I. This here was showed in the last lecture. Now this is stretch ratio. Now we can see that let's substitute. Okay. Now f dot e2 L0 and f dot e1 L0, just doing the dot product. So n1 dot n2 is equal. Now, the magnitude of n1 is 1. The magnitude of n2 is 2. So this will be cosine of theta. So theta is the angle between the deformed line L1 and the deformed line L2. Now it's important now a definition, to know the definition. Phi1 plus Phi2 is equal pi over 2 minus theta. This is called gamma 1 2 engineering shear strain. See? The engineer shear strain, you see, is pi over 2 minus theta. You see, is the sum of phi, in this case, Phi1 plus Phi2. So let's express now N1 and N2. Let's substitute the right hand side over here. Okay. N1 dot N2 is sine of gamma 1 2. And don't forget this, that cosine of theta is equal cosine of pi over 2 minus Phi1 minus Phi2. This is equal sine of Phi1 plus Phi2. This is equal sine of the engineering strain, the engineer shear strain, gamma 1 2. So from here we'll obtain right sine of gamma 1 2. And this here, you see, this is the vector dx at 1, this is the vector dx at 2. Now if you substitute by f dot capital dx, you see, capital dx on this line, you see, is the vector, is dx1 e1, and the capital the dx and this, the x2 direction is dx2 times the unit vector e2. So divide by L1 L2, because dx1, this here is dx1 and this is dx2. Now we can write sine gamma 1 2 is equal. Now you see there's a dot product, so we can do this. F, in this case, vector E1 transpose times F E2. You see? The dot over here. You see? Now this L01, L02, we can bring right here. You see, L1, L01 times L2, L02. This is stretch ratio. You can write down here, okay? This will be, now the transpose, okay? We have E1, F, transpose F, E2. So there's a dot product, okay, of this over here. And now this is stretch ratio. You can write the stretch ratio just as we did previously in the last class, the last lecture. This will be E1 dot G dot E1 times the square root of E2 dot G dot E2. You see, this is L1 divided by L0. L01 is this equality here. This is equal to this, and this is equal to that. Now, this is G. You see, that's G. Now, we want to know now what is E1 dot G dot E2. You see, this will be sine of gamma 1 2 is E1 dot G dot E2 divided by these two is square root over here. This is equal, okay? This is equal over here. Now let's do E1 dot G dot E2. And so sine of the shear strain gamma 1 is 2L1 divided by square root of 2L1 plus 1, 2L2 plus plus 1. And don't forget that this denominator here, okay, the last lecture, you see, we developed this. Now the numerator is 2L12. So why is 2L12? Because it's E1, G, this is G, okay? E2, okay? 100, G, 010, okay? Now, don't forget that G is equal to L plus I, okay? Now, if you substitute the elements of G is 2L plus I, we have 2L11 plus 1 over here, 2L22 plus 1 over there, and L33 plus 1. And this is well L12. If you multiply this, I'm sure you'll get 2L12. Now, if we consider the element dx1 and dx3, obviously we're going to get sine of 1, 3. And the element in x2 and the element x3, we are going to have a gamma 2, 3. This is in general gamma ij. This is shear stress. See, this is finite strain. Now, finite shear strain. Shear strain. You see? This is sine, the inverse of this term over here, this Lij. Attention here is no sum. No sum on I, and here, no sum on J. And here, see, look, see, now, sine, gamma 1, 1, 2. You see? This is 1, 2, this is 1, 1, and this is 2, 2. Now, this is a finite shear strain. And don't forget that Lij, in this case, okay, let's put Lij is equal 1/2 partial of Ui respect to capital Xj plus partial of Uj capital Xi plus, now the nonlinear term, partial of Uk Xi partial of Uk Xj. See? This is a Lagrangian second order tensor. The Lagrangian finite strain. Lagrangian finite strain. Finite strain. You see? From this Lagrangian finite strain, we can calculate the shear strain and the normal strain. Don't forget that the normal strain, L, on this new over here, you see, is equal, in this case, the stretch ratio minus 1. Don't forget that is dx minus capital Dx divided by dx. So this is the stretch ratio, dx, dx over dx minus 1.